Here are two kinds of things: blue on the left, pink on the right, and a clean gap between them. Your job is to draw a line that keeps them apart. Easy. Here's one. And another. And another. Every single one of these separates them perfectly. So they're all fine, right? Well, watch what happens when a new point shows up right here in the gap. Is it blue or is it pink? Tilt to this line and it's blue. Tilt to that one and it flips to pink. Same point. Its answer flips, depending only on which line we happen to pick. And we picked it for no reason at all. That should nag at you a little. If the data doesn't prefer a line, what does? So here's the whole video in one sentence. Out of all those lines, one of them is the safest, the one that leaves the widest empty street between the two crowds. And here's the part I actually want you to remember. Once you find that street, it turns out only a handful of points were ever holding it in place. You could erase almost everything else, and the answer wouldn't move. Widest street wins, and only the curb points get a vote. We'll learn that, slowly. Before we chase the best line, let's feel why most lines are bad. Take this one. It does separate the colors, but look how it almost grazes that blue point. It's cutting it close. Now, real data is never exact, so let's nudge every point just a hair, the way noise would. And there it goes. The line that was hugging the blue point now cuts right through it. One tiny wobble, and it's wrong. But this line over here, the one that left room to spare, survives the same wobble without blinking. So that's the lesson in one line. Don't hug the data. Leave yourself room to be wrong. Alright, room to spare is a feeling. Let's turn it into a number we can actually chase. For any line you draw, walk to the nearest point on each side and measure the gap. That distance, its closest call, is how much breathing room the line has. A line that grazes a point has almost none. A line sitting in the middle of the gap has a lot. So here's the idea, and honestly, it's the whole game. Instead of settling for any line that works, pick the line whose closest call is as far away as possible. Push the nearest point as far from the boundary as you can. One catch worth naming: a line doesn't change if you rescale the numbers describing it, so we'll quietly fix the scale by asking the closest points to sit at distance 1. Just bookkeeping. Here's a nicer way to see that same idea. Forget the thin line for a second and inflate it into a street, a band that grows outward evenly on both sides and pushes its two curbs apart. It widens and widens until it can't anymore because it touches a point on each side. Those points stop it. The width of that street is exactly the breathing room we were measuring, and it comes out to 2 over the length of that weight vector on screen. So whoever the street bumps into first is what sets its width. Hold on to those contact points. They're going to matter more than anyone else in this picture. Now we get to actually play. Pick an orientation for the street, any angle, and inflate. At this angle, watch, it jams almost immediately. 2 points on the same side crowd in and choke it thin. That's a bad angle. But turn it a little and inflate again, and now the street breathes wider before anything stops it. So the width depends on the angle. Some angles starve the street, some feed it. Which raises the obvious question. Somewhere in between there's got to be a best one. So let's just sweep through every angle and watch the width. Here's the street turning on the left, and here's its width plotted on the right, rising, peaking, falling. And there it is. There's exactly one angle where the street is widest, and when we lock it in, look where the boundary lands. Right down the middle, as far from both crowds as geometry allows. That's not a matter of taste anymore. It's the single widest street the data will allow, and there's only one of them. Remember all those lines we started with? The ones that made that new point flip between blue and pink. Here they are again, all of them. And here's our widest street laid over the top. Every one of them separated the data, but only one of them is centered. Only one leaves the most room, and that's the one we keep. So bring that new point back. Before, it was a coin toss. Now it sits clearly on the blue side of the street, and it stays blue. No wobble, no argument. Widest street wins. The ambiguity is just gone. Now lean in close to the curbs, because something strange is sitting in plain sight. Out of this whole cloud of points, only 2 or 3 are actually touching the street. Just these. Everyone else is sitting comfortably back from the edge, doing nothing. It really looks like these few points touching the curbs are the only ones holding the two sides apart. Let's find out if that's true. Take a point deep in the blue crowd, far from the edge, and just delete it. Watch the street. Nothing changes. It doesn't shift, it doesn't flinch. Delete another one from the interior. Still nothing. Delete a third. The boundary hasn't moved a millimeter. Now delete one of the points that was touching a curb. And there, the whole street lurches and resettles. So the boundary genuinely doesn't care about the crowd. It only cares about the borderline. Let that sink in, because it's genuinely surprising. The entire boundary is decided by just these few points on the curbs. So watch. Fade the rest away. Throw the whole crowd out. Keep only the 2 or 3 points that we're touching. And from just those, we can redraw the exact same street. Same line, same everything. You could throw away almost all of your data and lose nothing. Widest street wins, and only the curb points get a vote. If you don't believe me yet, let's just grab the points and pull. Take one of the points on the curb and watch. Drag it around and the whole street follows it. Live, like it's tied on with string. Now let go and drag one from the crowd instead. Pull it anywhere you like inside its group. Nothing. The boundary doesn't even notice. One quick honesty note. Since I called these points supports, they're not really pillars holding up a road. Pull a real pillar and the road collapses. Pull one of these and the road just slides to a new spot. They're less like supports and more like the fences the boundary has to squeeze between. So we've got 2 completely different kinds of point. A point in the crowd can wander around inside its group all day, and the boundary just sits there, bored. But a point on the curb can't move an inch without dragging the whole line with it. And notice the tally. Out of all these points, only a few of them actually get a say. The rest are just spectators. Now let me break it on purpose, because real data isn't this polite. Drop a pink point right in the middle of the blue crowd. Try to inflate a street now. It can't. There's no empty gap left to grow into, so no street fits, and the clean picture just falls apart. Here's the honest fix. Instead of demanding a perfectly empty street, we let a few points cross into it, or even onto the wrong side, and we make each one pay a small penalty. The rule becomes, get the widest street you can, while paying as little as possible for the troublemakers. Same idea, softened, so it survives contact with the real world. That's the version people actually use. So let's put names on what we built. The whole method, picking the boundary with the widest gap, is called a support vector machine. The widest street has a name too. It's the margin. And those precious few points on the curbs, the only ones with a vote, those are the support vectors. The whole thing is literally named after them. 2 honest edges before we go. In 2 dimensions, the margin really is a street. But with more features, it's a slice through a space you can't picture. The word street stops being a picture and becomes just a word. And safest only means safe if tomorrow's points look like today's. It's a smart bet, not a promise. One last thing, and it's a doorway. When you actually solve for that boundary, the data only ever shows up through the dot products between points, how aligned each pair is. Nothing else. Hold that thought, because some data laughs at straight lines. Here's a ring of blue wrapped around a pink core. Go ahead, try to split that with a street. Every angle fails. There is no line. But watch this. Lift each point straight up by how far it sits from the center. The core, near the middle, stays low. The ring, far out, rises. And now, in that one extra dimension, a flat sheet slides right between them. A street, one floor up. Here's the beautiful part. Remember, the machine only ever needed dot products. So we can get all the benefit of lifting into that higher space without ever actually going there, just by measuring closeness a little differently. That shortcut has a name, the kernel trick, and it's the whole next video. If your picture of these points shifted even a little, that's the win. Subscribe if you want the kernel trick next, and tell me down in the comments which kind of data you'd like to see it untangle.